Hello everyone, welcome back to another episode of Planet Hunters Coffee Chat. I'm Johnston and I'll be your host today, and joining us as always is Nora Eisner. Hi Nora.
Hi Carl. I just realised last week we didn't really do any introductions about you, so why don't you just tell us a little bit about yourself?
Well, I am a researcher, a postdoctoral researcher at Radboud University in the Netherlands. I am a bit of a star nerd. So I study all kinds of stellar variability. Anything that makes the amount of light that we see coming from a star change, like an eclipsing binary, some of the things you've been looking at, or other things such as star quakes. These are the things that I end up looking at. And I've got to say, as somebody who likes stars, it really hurts when you go into your false positive things and throw out eclipsing binaries.
I'm sorry!
They're really great stars, and it's unfair to throw them away.
Don't you also do something to do with gravitational waves?
Well, recently I have been I've been using an array of telescopes called the Black Gem Array, located down in Chile, to search for optical counterparts to gravitational wave events. And really what that means is that when we see a gravitational wave event, when two stars merge, we expect them to have give off some kind of light. We're not entirely sure what that's going to look like all of the time.
Like a supernova?
Like that, but a lot smaller.
Okay.
So we actually call them kilonovae, when two neutron stars merge.
Okay.
So not quite super, but still kilo. And we look for these bursts of light, and then I try to find them, and we try to model them after that.
Ah, it's fascinating. It's a lot larger scale than what we do with the planets. All right, well, we do have some more things to talk about with partly planets today, partly not planets. So why don't we start with that? So we're still part of our mini-series of looking at false positives, and this test can be used for that, but it can also be used to look for other fun things.
Oh, okay. So what else are we going to be hunting for today?
Asteroids.
Oh, okay. Let's get to it.
Asteroids and systematics is what we're after today. All right, we'll get to the asteroids part in a moment, but first I will just show you the test. All right, so the test that we have today is, I call it the nearest neighbor light curve plot. And maybe that name is a bit misleading, but we'll also get to that in a moment. So what we have here is in the top panel here in red, we have the light curve that we're looking at. This is the one that we probably selected. This is the star that we were interested in. We can see we have a dip in here, a transit-like event. And underneath we have light curves of nearby stars. Now the reason why I said it's a little bit misleading is because they are nearby stars in the sense that they were the closest stars that were also observed by TESS in the 2-minute cadence. But a lot of the time they are not actually that nearby. So there are always stars that are a lot closer than these stars, but these are just the nearest stars that have the same type of light curve available for them. And what's cool about these is that we can look to see whether there are kind of similar events at the same time of the event that we see in the light curve that we are interested in. So we're making sure that there are no transit-like signals at the exact same time in all of the other light curves. And the reason why we're checking this is because we want to make sure that that transit-like event is not caused by a systematic event. So systematic could again be a TESS, for example, jolting slightly, and that could affect lots of light curves. Even if they're not really close by to one another, it could affect light curves that are observed by the same TESS camera. So we're just making sure that there are no large-scale systematics happening at that time.
Okay, that's good to know that these are things that are kind of nearby on the sky, and just by looking at what's happening in their light curve, if we see the same event in multiple of these panels, then we would know potentially it's a systematic. So this is still another one of these vetting tests that you've been going through, correct? Yeah,
this is definitely one of the vetting tests. In all honesty, I wouldn't say this is the most important one. This is just another one that we do for kind of a sanity check. But it's not we don't rule out a lot of false positives based on this test.
Now, I'm just looking at this really quick. I notice on the side, on the right, there's a lot of different numbers.
Yes.
So you've so if I can see you have the first set of 1287, and that's the tick ID, the test input catalog ID for the target. Then you have the brightness, right, the test magnitude, and then I see D, which I believe is distance, right?
Yes, so that's the distance to the target star. So I should also say it's not an actual distance, it's a projected distance. It's the distance we see on the sky. Okay. If you were to travel between these two stars, it would be a different distance. But because we're seeing it as a 2D image, we see all the stars projected as a 2D kind of points on the sky, as opposed to the 3D. This is just the 2D distance between them, so kind of the projected distance on the sky. And we can actually show that on here. So here's a little kind of image of the cutout around that area, and we have the kind of the light curves next to where I've drawn a little circle around where those stars are. You can see, now that we have Cole here, we should really talk about some of these stars that we see here. We see some nice eclipsing binaries, I want to say, and maybe Cole can talk a little bit about this blue one up here. I would say it's a chemically peculiar star.
Yeah, well, that could be something that's chemically peculiar, and what we mean by that is that when we normally look at stars, their surfaces are homogeneous. You can't tell one place, you can't tell it apart from another, and just a uniform brightness. But sometimes, especially in heavier stars or hotter stars, what you can find is that there are dark spots on the surface, and those dark spots are caused by buildups of different chemicals, very often heavier elements that are held in place by a magnetic field. And then as the star rotates, what you see here is that dark spot comes into and out of view. So you see it, then it goes out of view, and then it rotates back into view again, and that causes the changes in brightness. Now, looking at that blue one, there are going to be a couple of spots that hold that same pattern. That's one potential explanation. This also could be another eclipsing binary. So you don't actually see, maybe eclipsing binary is not the right way to put it, but it could just be a binary. And what you can see from that is that you have two stars, and they're so close to one another that they're no longer spheres. They kind of deform one another so that you see them as a sphere from this point. Now they look kind of football shape or teardrop-ish, and then they look spherical again when you look at them just right down the middle. And this is going to cause a change in the amount of light that you see as they go around one another. So
would both of the stars in the eclipse or in the binary be distorted, or just one of them?
It can be both of them, one of them, neither of them, but in this case, because we can see that there are two different dips of different height, I'm going to go ahead and say both of them.
Ah, very cool. See, this is why we need Cole to come back to talk about stars. But we're going to look at where these stars lie on the sky. So I'm actually going to get rid of these light curves because I think they're a little bit in the way. And instead, let's have a look at kind of the scales of what we're looking at here. So this is just kind of to drive home the point that these stars are not close by to one another, even though they are the closest stars to one another that Tess also observed. So down here we have roughly to scale, the moon. It's around 1/2 degree across if we look at it from the Earth. And just above it, that little square that we see here, the 11 by 11 pixel cutout, that's usually the kind of cutout that we see around stars. So in previous episodes we had those images where we had the brightest star in the middle, that was our target star. And we just had the pixels around it to show kind of the surrounding area. So that would be the size of one of those cutouts. And as you can see, these stars don't fall on the same cutouts. They are very far away from each other, as you can see here. But it is still useful to check the light curves of these stars, even though they don't seem like they're that close. And the reason for that is we can see an example of where we could use this test as a false positive test. See, in the top light curve here, we have another kind of transit-like event here at the start where that black line is indicating it. And then if we follow down, and we can't see anything in the orange, we can't see anything in the yellow, but in that green and the blue light curve, these two light curves here, we can see very similar dips at the same time. So these dips are probably or most likely caused by something happening to multiple pixels on Tess or to the same camera. That just caused there to be a slight dip in the light curve at a given time. And that would be then called or ruled out as being a systematic event. And we might be able to see this in some of the other tests as well that we already looked at. For example, the centroid test that we covered last week. All right, on to something different, what we can also use these for. We can use these to track asteroids. And I think this is really cool. So bear with me as I get very excited about this. So in the top light curve, this is the light curve that we flagged first. We have this spike in the light curve, and we don't think this is a planet. At no point did we think this was a planet. We expect to see dips when we look for planets, not spikes. Nonetheless, it was cool, so we looked at it, we made these plots, and you can see these spikes appearing in some of the nearest neighbor light curves. You see it in the orange, you see it in the blue, you see it in both blues and in the green. So something is affecting lots of different light curves around the same time. So what we can do is we can look at where these stars lie on the sky and mark them on like this. And then you can actually draw kind of a line through where an asteroid would have moved through. Now let's play that again, maybe a little bit slower. That's the same speed. We can now kind of jump through it. So if we go to the point where it's now on the orange light curve, this is where it's coming from. This, in terms of time, we see the spike first in the orange, so we know it must be coming from this direction. We can then fast forward a little bit more, then it hits the red, that one's next, that's the next spike there. And we can move forward and then it hits the green and the blue. So we can kind of draw on a kind of path of this asteroid moving through the field of view. And you can see it affecting multiple light curves, which I think is quite cool. And we can then take this one step further and we can say, okay, it hit the orange one at time equals 0. Arbitrary time, doesn't matter what the time is, we'll call it t equals 0. We then say, at what time does it hit the red light curve? This is the top one, it's drawn on in pink over here. It hits it around 20.2 hours later. Now, we can then go forward a little bit further and we can say what time does it hit the green, what time does it hit the blue, and from that, you can then work out the projected distance across it, or between these stars, and the time between them, and with that you can work out a projected speed of this asteroid on the sky. Which I have to be honest, I didn't do anything with after I've done that, but I think it's very cool.
Okay, so you just felt reminiscent of those maths courses that you took back in high school where you just needed to figure out the speed at which something was traveling?
I hadn't taken an exam in a while, so I figured this was the right time to bring back those math skills.
Okay, I mean, it's a good application. Whenever somebody asks you, what are you going to use this for in the real world? You can use this math to see how fast an asteroid is moving across the sky.
Yeah, so this is another thing you can do if you find one of these spikes and you are interested in seeing whether that could be an asteroid or what that path of that asteroid is. I should very quickly point out these maps, so these ones that you can see here, you can find these on Sinbad and download them and look for the stars. And I should point out, it's sometimes very difficult to find which star is the right one. So you need to carefully match different maps on top of one another. It's like a big game of spot the difference. But actually you're trying to spot the same star, not the different star.
So stellar, where is Waldo?
Exactly, yes. Now that I'm thinking about it, we could actually get the next field of view. I only looked at the next couple of stars. We can get the next field of view and try and track this asteroid.
That could be something that a particularly interested viewer could do.
Yeah.
Post it in the comments, see if they can find out what the next field is, or the adjacent camera, and see if they can continue tracking this asteroid's path through the sky.
Yeah, let's see where it goes. It's a great idea. Or yeah, if you find another asteroid or something else we can track with these types of light curves, then do leave a comment, and we'd love to hear about that. That'd be really cool. So I also, just before we finish up, I want to say that this is kind of the last test that we'll be covering in these false positives, but in the next episode we'll be going over very briefly all of them again, and we'll be showing you a tool called LATE, or the Light Curve Analysis Tool for Transiting Exoplanets, which is a tool that automatically generates all of these plots for you. So you just have to enter the ID number, you have to tell it where the star is, what sector you want to look at, and it will make a PDF format file report for you with all of these plots in them. So we'll go over those next week, and hopefully they could be very useful if you're interested in ruling out false positives. So
I think we should say thank you very much, Nora, for the time and the fun discussion about finding planets and or asteroids. And I guess we'll see you next time. Bye, Nora.
Bye, Cole. Bye, everyone.